All right, so if you've gotten pretty comfortable with single and double integrals, you're ready to take the next big step, literally, into the third dimension. Today, we are diving into triple integrals, a seriously powerful tool for figuring out the properties of 3D objects. Let's get right into it. So let's start with a real-world question. How would you find the mass of a 3D object if its density isn't the same everywhere? Think of a piece of metal that's not perfectly mixed, or even something as big as a planet. Simple multiplication just won't work, and a double integral can't handle it either. This is exactly why we need something more. And the solution, you guessed it, is the triple integral. It's really a natural extension of everything you already know. Remember how single integrals add up tiny little lines to get an area, and double integrals add up tiny areas to get a volume? Well, a triple integral adds up tiny little volume cubes, we call them dV, to get a property across a whole 3D region. So, what can we actually do with these things? Well, they're super useful in both geometry and physics. We're going to focus on the two big ones, finding volume and finding mass. And the difference is surprisingly simple. It all comes down to the function you stick inside the integral. As you can see here, if you integrate the number 1, you're just adding up all those tiny volume bits to get the total volume of the shape. Easy enough. But if you integrate a density function instead, you're adding up the mass of each tiny bit to find the object's total mass. It's that simple. The function you integrate is the property you find. All right, here's where things can get a little tricky, and it's where most people get stuck, setting up the limits of integration. This is, without a doubt, the most important and often the hardest part of the whole process. But don't worry, we've got a simple mental model that's going to be your blueprint. Here's the key idea that unlocks the whole thing. The very first step is to visualize your 3D solid and think vertically. I want you to imagine shooting a laser beam straight up through the object. The first surface it hits on its way in, that's your floor. The surface it pops out of, that's the ceiling. These two surfaces are what will define the limits for your innermost integral. Now, this floor-to-ceiling concept has a formal name in math. It defines what we call a type I or Z symbol region. The floor is represented by some function u1 of xy, and the ceiling by another one, u2 of xy. And as you can see in the formula, those become the limits for your inside integral, the one with dz. And that's exactly why you always solve that one first. So once you've dealt with that vertical z dimension, what's left? This is the really cool part. You basically just squish the 3D shape down into its 2D shadow on the xy plane. And just like that, you're left with a standard double integral over that shadow region, which is something you already know how to do. It's a brilliant way to turn a complicated 3D problem into a much more manageable 2D one. Okay, enough theory. Let's see this blueprint in action. We're going to start with the most straightforward 3D shape there is, a simple box. So here's our problem. We need to find the mass of a box with these specific dimensions for x, y, and z. Now, take a look at the density function, rho equals x plus z. Since the density actually depends on where you are in the box, it's not uniform, and that right there is why we need to use a triple integral. Setting up the integral for a box is about as easy as it gets. Because all the boundaries are constants, the limits of integration are just the dimensions of the box. So z goes from 0 to 3, y goes from 0 to 2, and x goes from 0 to 1. We just pop our density function inside, and we are ready to go. And how do we solve it? Always from the inside out. First, we'll integrate x plus z with respect to z, just pretending x is a constant for now. Then we plug in our z limits. We take that result and integrate it with respect to y. And finally, we take that new result and integrate it with respect to x to get our final answer. And after you run through all those steps, you find that the total mass of the box is exactly 12. So this first example really shows you the basic mechanics of how this whole process works. Okay, that was a good warm-up. Time for something a bit more challenging. Let's move on from a simple box to a shape where the limits are not going to be constant numbers. Let's tackle a tetrahedron. This will really put our blueprint to the test. So try to picture this shape. It's like a pyramid in the corner of a room, bounded by the floor and two walls, and then sliced off by a slanted plane, x plus y plus z equals 1. And since the problem is asking for volume, that tells us the function we're going to be integrating is just the number 1. Okay, let's pull out our blueprint and build this thing step by step. First, the vertical limits. The floor is the xy plane, right? That's where z equals 0.
The ceiling is that slanted plane. So if we solve its equation for z, we get z equals 1 minus x minus y. Boom, those are our inner limits for dz. Next, we project the shadow of this shape onto the xy plane. Setting z equals 0 in that main equation gives us the line x plus y equals 1, so the shadow is a triangle, and that gives us our outer limits. Y goes from the bottom edge, 0, up to the line 1 minus x, and x goes all the way from 0 to 1. And that's it. That's the complete setup you see here.
The solving process is exactly the same, inside out. But here's the key difference. This time, when we plug in the limits for z, we're left with an expression that has x and y in it. Then, when we integrate that with respect to y, we have to be super careful substituting that 1 minus x limit. See how each step just peels back one dimension at a time? And when all the dust settles, the final result for the volume of this tetrahedron is 1/6. This is such a classic calculus problem, and now you can see exactly how it's done from start to finish.
Okay, let's just step back for a second and really make sure this process is locked in. This is your repeatable blueprint that you can use for any triple integral problem you come across.
This is it. This is your mental checklist. First, always try to visualize the shape you're working with. Second, find your vertical limits, your floor and your ceiling, for that first dz integral. Third, project that 2D shadow down onto the xy plane to set up your double integral. And finally, just calculate everything from the inside out. Follow these steps and you will always have a clear path to the solution.
You know, we focused on mass and volume today, but this tool is so much more versatile than that. Just think about it for a second. What else could you figure out by adding up tiny properties over an entire volume? You could find a shape's center of mass, its moment of inertia for rotations, or even its average temperature if you have a temperature function. Triple integrals open up a whole new level of physical and engineering calculations. The possibilities are huge, and now you have the blueprint to explore them.